So tonight we're going to be learning about cell membranes and cell walls in archaea and bacteria. Obviously this relates to the lab that you started today and will be continuing tomorrow. Alright, so first off we have the archaea cell membrane. This is made of lipids, which are fats, and they are glycerol hydrocarbon units linked together by ether bonds. And these are actually really strong setups. They hold together even at really high temperatures and other extremes. So as you can see, they're bonded together quite firmly. This is the ether linkage, the carbon, oxygen, carbon setup there. Okay, so that's archaea. Remember that they live in extremes, so this sort of makes sense for them. Alright. Bacteria, on the other hand, have glycerol fatty acid units linked by ester bonds. And so this is an ester here, where we have carbon, oxygen, carbon, double bonded to an oxygen, and then more carbons over there. And as you can see, this is not connected in quite the same way that the archaea one was, because there's this break here. Alright, so if we look at them side by side, you can see that the archaea is much more solid. So it's going to be a lot stronger. On the other hand, this bilayer with the bacterial cell wall, and also common to eukaryotes, is much more flexible, so it has sort of more options. And obviously these are adapted to different environments, and so there's different advantages and disadvantages to both. Okay, so the bacterial cell wall, what is it made of? It's made of peptidoglycan, which includes alternating units of NAG and NAM, or NAG and NAM. And so again, peptidoglycan, it's made of amino acids and sugars. And it protects and supports the bacteria against their changing environment, just like your skin protects you. This is their skin, pretty much, their cell wall. Or it's almost more like a coat. Alright. As you can see, the peptidoglycan sheets, they layer on top of each other for extra protection, and that creates a more secure and solid cell wall. Some bacteria also have this extra layer called lipopolysaccharide. So again, that's lipo is the lipid or fat, poly is many, and saccharide, we're back with sugar. So this is known more conventionally as LPS. You don't have to say lipopolysaccharide all the time. That is kind of fun. So basically some bacteria have this. It makes them more resistant to antibiotics. It's also an endotoxin, so that means that when a bacteria with LPS enters mammal body, it can cause fever, it can cause inflammation, it can destroy blood cells, it can cause shock, and even death, because the immune system sees this and really reacts quite strongly to it. So this can be a huge problem when you're infected with something that has an LPS layer. Alright, so just to compare, we've got the gram-positive with just peptidoglycan, and we've got gram-negative over here. We've got the peptidoglycan, and then we've got the LPS layer. And you can see how much bigger and stronger this would be, and how this would really protect a cell against a lot of different things in its environment. Okay, so we've been gram staining. So we've got gram-positive, and that, again, are those crystal violet ones. And those only have peptidoglycan. And then we have gram-negative, and that's where the safranin has bound. And those have the peptidoglycan and the LPS. So you can see crystal violet would have bound in the first round, and then it wouldn't have rinsed off. And here, the crystal violet couldn't bind, so it rinsed off, and then the safranin did die later on in the process. Okay, so gram-positive are purple, gram-negative are red. Cool. So there's even more layers to this. Most bacteria also have something called a glycocalyx, which comes from the Greek glykos, meaning sweet, and calyx, meaning husk or cup. And so this is a sugar coating, made, of course, of polysaccharides, so more sugar. Yep. And this helps cells adhere together. So think about if you spill ginger ale all over your hands. They're going to be very sticky and stick to each other. You'll stick to surfaces. It's kind of gross. But if you're a bacteria and you don't have arms and legs and hands and feet, you can't really hold on to things that easily, so being sticky really helps. You can get onto surfaces that are good for growing, or, hold on to cells of, say, a human body, if you're trying to get into their intestines or something exciting like that. So what happens if a glycocalyx is actually pretty tightly wound around the bacteria? then it becomes a cell capsule. So it's just like a very tight coating of this sugar. And this can protect the bacteria from digestion and protect the bacteria from the immune system of any host that it is in. And this can really help. I mean, it's a thicker, more tightly bound layer, so it's more protective, but then it's going to be less sticky because obviously loose things have more surface area to stick together with. Alright, so leading from that, if you have a really loose glycocalyx, then you're going to be super sticky. And this is called a slime layer. And some bacteria actually use this to move. By having this very loose skin, they can, or loose cell wall, they can become very sticky and use the stickiness to sort of roll around and move. There's also a more typical way that bacteria move, which is they have in common with eukaryotes. It's called a flagella. Remember learning about sperm? They have flagella. It's a long thread-like appendage, so you can see you can have different sort of combinations and locations of flagella, and they all obviously work in different ways. This is going to move a little bit differently than this guy. And some bacteria, they don't move. It's not really in their agenda, so they don't need to. They're fine. So if we go a little bit more into the flagella, you can actually see this is an x-ray of the base part of the flagella that rotates it. And it looks like a machine. It looks like something out of like a mill or something. And if you look closely at it, you can tell that its base is stuck in the plasma membrane and then it goes up through different parts in the cell wall and in the outer membrane. And this whole base turns, which in turn twirls around the filament. And flagellum comes from the Latin for whip. It's basically whipping around because that's the motion that's happening. And if you look at this, it's powered by a proton pump. So if you see those hydrogens, that's H+, as that moves in and out, it makes this whole section turn. And just if you ever think that humans invented anything, like bacteria got here first, they have essentially a mill. You know, they have a gradient, just like a mill would have water going downhill. And it powers movement of something turning, like a wheel. It's crazy. Anywho. Next up, bacterial shapes. So we've got three basic kinds of shapes. We've got the bacilli, which are kind of long, rod-like. We've got the cocci, which are nice and round. And we've got the spirilli, which are spirally looking. Alright, so bacilli, cocci, spirilli. Next up, you can have two different arrangements of the different kinds of shapes. So you can have staff, which would be a cluster. So these are staff because they're clustered together, and then they're cocci because they are round. So this would be staphylococcus. Or you can have strep, which would be chains. So if you look at these guys, these are bacilli, and they're in a chain formation. So that would be streptobacilli. So again, bacilli, cocci, spirilli. So if you're looking at this, this would be a staphylospirilli because it's clusters of spiral organisms. Okay, so that's pretty much it. You are going to see all of these in lab. Some of them you probably saw today, and some you'll see tomorrow. Alright, great. Have a good night.